Oh, recording in progress. Good. Hello. Right. Okay. Today we finish organic chemistry. I'm going to do some chemistry on the wall behind me. We are going to look at the things that we finished with last time, which was soaps and detergents and polymers. I'm going to do a little bit on the wall behind me in a moment. And then I'll take any questions on that. And then we're going to do a little quiz which you could either try on your own or in pairs, or you could each center could try to split into some little teams and you could have a go. There are only, I think, 13 questions, but it will take a little while. So I'm going to start with the information that I said last time was quite important, which was the bits and pieces to do with Form 4 chemistry, which was the soaps and detergents, polymers, and there's a little bit on making tires out of rubber and sulfur. So we're going to do those. I'm going to do them on the wall behind me in just a moment. I'm just going to change my camera, hopefully. Oh, I'm not there. Where am I? Oh no, I've disappeared. Hello. Right, so I hope you can still hear me. I know I'm a little bit low because my screen is very big. I've had to stick some plastic on a wall because I can't get into my laboratories because other people are using them. So the first things are to do with soaps and detergents. And if you remember, we said they look very, very similar. And all I want you to do is to think that you just have to recognize one thing about soaps and detergents, which is about how their structures compare. And I'll just show you now. So they both have long chains. It doesn't matter what the long chain looks like. Hang on, let me just close the curtain so there's less reflection. Okay, I hope you can see that. I'll make it a bit darker. So they both have very long chains of carbons, and it doesn't matter what those long chains are. It's just carbons and hydrogens. Sometimes they will make it look more difficult than it is, but at the end of a soap, you have this. This here, C double bond O, and then the Na, it's actually charged, minus and plus, but that's not important. What is important is that this is a soap. It's not a detergent. A detergent has something different. And the thing at the end of a detergent is a sulfur. So carbon for a soap and sulfur for a detergent. And it's actually something that looks like this. This doesn't matter. What I want you to do is to remember this is not the soap. This is the detergent. Carbon on the soap, sulfur on the detergent. Now, what you have to do is to be able to recognize those and then say which is better in certain circumstances. So the first thing to remember was that both of them work to dissolve dirt. Okay, the polar end of the molecules will try to get into water. Polar things dissolve in the polar solvent. The water is polar, so these dissolve in that. And the non-polar bit of the chain, which is just carbons and hydrogens, sticks into the dirt. So if I get some oil or grease on my hands and I try mixing it with water, nothing happens because the grease is non-polar and the water is polar, so they won't mix. If I add soap or detergent, then this end of the chain will stick into the oily waxy bit, and then this will drag it off into the water. So this takes it into the water. Now, there is one advantage and one disadvantage of each one of these. The advantage of the soap is that when it goes into the drains and the rivers and the seas, it breaks down, it is biodegradable, and it will break down really, really easily. The detergent does not break down very well at all. In fact, where I live, we quite often see foam on one of the rivers, and that foam is detergent not breaking down properly. So the advantage of soap is it breaks down easily. The disadvantage of the detergent is that it doesn't break down easily. The advantage of the detergent is, firstly, it is a little bit better at dissolving the dirt and so on. But its advantage is that in hard water, it doesn't form scum. If you take hard water is not harder than soft water. They are silly words, really. Hard water contains calcium or magnesium ions in it. It has normally come by going over limestone or through limestone when it forms. There's a disadvantage to that, and that is that some of the calcium or magnesium dissolves into the water, and this doesn't make any difference to the detergent. So the detergent works perfectly okay, but the soap doesn't, because what happens is that the soap, the sodium is kicked off and calcium ions stick to it, and they make a scum, and the scum will stay. So for instance, if you have a washing bowl and you wash your hands with soap and it is hard water, round the edge of the bowl you will get scum, like it doesn't look very clean. That means that if you wash your clothes in a hard water area with soap, they will not get completely clean. You will get rid of the oil and so on, but you will be left with scum on it. Okay, that's the first thing. So that's the soap and detergent that I mentioned last time. Okay, anybody got any questions about that? Anybody want to come back about that? I'm just going to go back to my other camera just for a moment. So I've disappeared and I'm about to reappear through the magic of computers. Hi, has anybody got any questions about detergents or soaps? Anybody got any questions, or is that sort of okay? Tell me, are we okay, or are we, no. Are we okay? Genesis, okay. Ushirika, show me you've got thumbs. That's excellent. Silver Spring, are we okay? Silver Spring, are we okay? Cool, excellent. Kabiro, welcome. I hope you can see me. I can't see you, but it doesn't matter. Okay, I'm going back to my other camera. So we're going to talk about polymers now. Okay. There are two different types of polymer. There are many, many different types of polymer overall, but they are divided into two classifications. And the one I'm going to tell you about most is about what we call an addition polymer. An addition polymer is always formed in the same way, and that is from an alkene. Alkene, double bond, if you remember when we were talking about it, a double bond is stronger than a single bond, but one of the bonds is really quite strong and one of them is quite weak. So the second bond can break and join on to other things. And that's really important as an idea. And alkenes, I'm going to take the example of ethene. So if I have ethene, and I have many ethenes, so I'll draw a couple more. I'll just draw them across here. If they are heated and put under pressure, what happens is that one of the bonds breaks. When that bond breaks, it looks for something else to join onto. And what happens is this. This one breaks and joins on here. This one breaks and joins on here. This one breaks, and so on. And there is a simplified way of writing that. And that is, if I say I have ethene and I have a certain number of them, N of these, it turns into this. So what we draw is a little section of the polymer like this, and we say, it goes on, and then we put brackets around here and put the N there. Okay, so this is the monomer. I'll just get rid of the stuff up above so it's not confusing. So here's the monomer, mono 1. Here's the polymer. And the monomers, one of the bonds breaks and joins onto the next ones either side, left and right. If I start with a certain number of them, I end up with the same pattern repeated that many times. Now, the idea of this is that we can change the polymer by changing the monomers. It always works in exactly the same way. So if this is ethene, then it makes polyethene. Okay, so you probably know this anyway, but I just want to go through it because it makes it much more obvious when you come to the examinations. Now, this is sometimes called ethylene, but most of the time we call it ethene. The monomer is ethene, and we just put the word poly in front of the monomer's name for it to become a polymer. If I want to change the properties of the polymer, in other words, I want to make something different out of it, this was used for plastic bags, which you may remember 4 years ago, 5 years ago, were banned in Kenya before anybody else. Then all I have to do is to slightly change the monomer. For instance, if I take one hydrogen off and instead of ethene I put a chlorine on, then this is now chloroethene. So it will be polychloroethene, and every second carbon will have a Cl on it. Polychloroethene is commonly known as polyvinyl chloride, or PVC, which they used to make records out of. They still make materials out of, and they also in this country make a lot of window frames and doors where we're trying to keep out the rain. So this is it's quite a good rigid plastic without being too fragile, without being too brittle. Now, so all you have to do is to be able to write the monomer and turn it into the polymer, or often the other way round. So I'll give you an example. So this is a different monomer, makes a different polymer. And if I look at this, let me make this into something different. I'm going to change it completely. This is something called Teflon, which is used to make non-stick saucepans. And what they often do is they show you a bit of the polymer. Sometimes it's like this, and sometimes it's an extended piece of it. And you have to work out what the monomer is. So all you do is you look at that and you say, well, hang on, there used to be a double bond there. So I'm going to go, okay, CC, it's got 4 F's on it. That's easy. That must have been the monomer. And that would be true if I did it like that, or if they showed you a bit like this. So I'm going to make this look a little bit more complicated just now. So what they often do is they show you a longer section of the polymer like this. And so it looks like it's not quite as obvious what the monomer was. But what you do with it is you just remember it is always 2 carbons. So I find 1 carbon here and I draw a line and I say, okay, that's where I'm going to start. I'm now going to move on 1, 2, and draw another line. And that is the repeating unit. That's the bit which is the same on and on. Why 2 carbons? Well, because I need a double bond in the monomer to make it. So I look at that and I say, oh, C, 2 Fs, double bond in the middle. This must have been the monomer. The last thing that they do is that they sometimes say, work out how many monomers made the polymer. And I'll give you an example. So let's say I'm taking ethene, and I'm going to turn it into polyethene, which is C2H4N, and I want to know what N is. Let us say that they take the polymer, a strip of the polymer, and they work out what its RMM is. And let's say its RMM is 28,000. And what they say is, how many monomers went into the polymer? Well, what you do is you say, okay, what was the RMM of this? This is 2 carbons. Each carbon weighs 12. 4 hydrogens, 1 each. So 2 times 12, 24. Add 4, 28. So the RMM of that is 28,000. The RMM of this is 28. How many of these in there? Oh, well, 28,000 over 28, 10,000. Okay, that's quite simple. All you do is you take the RMM of the polymer and divide it by the RMM of the monomer. Okay, I'm coming to my other computer. Other camera. Okay, any questions so far? Are we okay? Usharika, you're looking very bright today. Are you feeling okay? Genesis, you have the best thumbs. Genesis win on thumbs. Silver Spring, are we okay on that? Is that okay? Kabiro, is that okay? Because you're going to be needing it in a little bit. Oh, some people at Kabiro not quite so happy. Okay. Not quite so happy. Please mute whoever is unmuted. That's fine, it's gone. Okay, I'm going to send some PowerPoints. Silver Spring, can you mute, please?
Excuse.
Hang on just a minute. If you have a question, Silver Spring, just hang on just a moment. Kabiro, I will send some PowerPoints which will tell you more about organic chemistry and our recordings from other lessons we've done. And then perhaps if you missed it, you will be able to see it and work it through yourself, okay? Because I think you will all be at different levels. There are some people at Silver Spring, some people at Usharika, some people at Genesis particularly, who are very, very good at chemistry and have done lots of it. And some of you won't have done quite so much, and that's difficult. But if you watch these, you will find that many of them, you only have to watch a little bit of it. Hello, Glory. How nice to see you. Good to see you, Glory. Is it very cold there? You got lots of clothes on. I guess it's only 26 degrees. Here today, it's, I don't know, 16 or something ridiculous cold. Anyway, so that's polymers. Silver Spring, did you have a question? You unmuted. Did you have a question? You unmuted. Did you have a unmuted?
Okay, as you were calculating those mathematical issues, I noticed that you used 28,000. Where was it from?
From a question. It's a good question. Mute yourself again, please. In a question, it would say a polymer made from ethene has an RMM, is found to have an RMM of 28,000. In other words, I just made up a question. So they would say in the question, the polymer has an RMM of 28,000. It is formed from ethenes. How many subunits or how many monomer molecules went together to make it? Okay, so it's something that I just made up. Okay, I'm going to go back to my other camera and my board. hopefully. Okay, the last bit of the particular bit of chemistry which we're doing on this, the last two bits, sorry. One is about what we call the vulcanization of rubber. Rubber is a natural polymer. It has many double bonds in it. It comes, as you know, from a tree, and it is long chains. Now, the long chains tend to stay together because of intermolecular forces. So if I have long chains and they're just carbons and hydrogens with some double bonds in and so on, then the reason that polymers tend to be solid is because they get a bit tangled up. And as they get tangled up, the intermolecular forces hold them together. But intermolecular forces aren't very strong. If I take this pen is made from plastic. The intermolecular forces in this are not really very strong, so that it's relatively bendy. The plastic which covers it can be pulled off quite easily. It just breaks. And it breaks because the chains in it are not held together very well. When we take natural rubber, and they started using natural rubber to make tires for cars when they invented the automobile. And what they found was that the tires would break really, really suddenly, unexpectedly. So they had to make them harder. And the way that they made them harder was to do something called vulcanization. Now, Vulcan was the Roman god of war, and also it's to do with heat. And you may have come across the word volcano, which can help you remember it. But vulcanization is a process of heating up these chains. Now, heating them up on their own doesn't work. It doesn't do anything. It just melts it. But they put in a certain amount of sulfur. And what the sulfur does is it joins between chains. So we get a sulfur atom joining one chain to another. It's what we call a cross link. A cross link can form quite regularly, depending on the amount of sulfur that we add and how long we heat it. We might have more or less cross links. If you think that the chains are very flexible, then the more cross links I put in, the less flexible it becomes. If I do it too much, it becomes inflexible, and we want a tire on a car to be able to absorb the shocks of the road. Perhaps not the new road right the way through the middle of Nairobi, but perhaps if I was going out to Kisumu or something, I might want quite a lot of flexibility in my tires. So I want to put in the right number of cross links and not too many. So it is sulfur. I haven't shown the sulfur in each one of these, but each green line means there is a sulfur there. So it's heat with sulfur. That's the important thing. And the point is that it makes the tires, they are still quite sticky, which we want, so they will stick to the road, but they are a bit stronger and a little bit more reliable, so they won't break so much. In fact, if you get a tire truck, truck for a tire for a truck, and it wears down the tread, you can actually take a knife, because it's so thick, you can take a knife and carve new lines in it, which will give it more grip again. You can't do it forever, but you can do it several times. So this is vulcanization. Okay, they come up quite regularly, both in questions about sulfur and questions about organic chemistry. So it's all about just making the rubber a little bit more resistant. Okay. So the last bit I want to suggest that you do, and this is something that we did last time. I want you to try, when you are looking at this in revising, I want you to do what we said last time, which was to go, okay, I've got an alkene here. I'm going to have an alkanol here. I'm going to have an alkanoic acid here. And I'm going to learn and I'm going to remind myself how I go from an alkene to an alkanol back to an alkene, an alkanol to an alkanoic acid. These two both, if you remember, both come down to form an ester, the very pleasant smelling chemicals. What I want you to do when you have some time is to draw this out. We also had alkane up here, and that can go that way and this way. We had another way of making an alkanol, and that was from a sugar. And we also had alkenes to polymers, which we've just looked at a little bit here, like that. Now, if you can remember this picture, then you can test yourself. You can go, alkene to alkanol. Oh, no. Yes. And then if you can remember just one example, it will help you. So if I think alkene and I think, okay, I'm going to go for a 2-carbon alkene and a 2-carbon alkanol. Alkenes have double bonds. Okay. Each carbon has 4 bonds. 1, 2, 3, 4. Oh, yes, it's ethene. Alkanols have single bonds and OH. Okay. Now, if I count up between here, which is C2H4, and here, which is C2H6O, there's another oxygen and 2 hydrogens. That must be water, etc. So I'm going to suggest that you need to have something like this that you write out for yourself, so you get used to how they do things, how the reactions happen. Alkanol oxidized to an alkanoic acid. Alkanoic acid and alkanol to ester. We need some concentrated sulfuric acid, if you remember. But it will be in the PowerPoint from last time, which I'm going to send to your supervisors. Okay, I'm going to come back to my other question, my other camera, but I'll leave that there just for the moment. Okay, so this sort of thing, I think, is the way to remember and learn how to make one organic chemical into another one. I think it's the way which will make life a lot easier for you. But now what we're going to do is, because we are now at the end of organic chemistry, we are going to have a little quiz. And I encourage you just to write down your answers, to think about your answers. You can keep your score. There are only 13 questions. That's lucky. And some of them are about what is this chemical. Some of them is how would you change this one into that one, and so on. And you will get a copy of this PowerPoint afterwards, and you can look at it on the recording. Each one of my recordings, each one of the recordings, and there are quite a lot of them now, are on YouTube, and I have sent the details to your supervisors, so they're all there, and you can look at any of them. They're pretty boring. I look at them occasionally, I go, oh my gosh, that was terrible. Anyway, some of them have how to do a practical, which is quite useful. Okay, so what we're going to do now is I'm going to suggest that you, like in Ushurika, they have 2 sides of the table. So let's have the left-hand side of the table against the right-hand side of the table, or in pairs or something like that. Have a go at these questions. Let's have a go. Okay, here we go. So I'm going to share my screen now. I hope that you can see my my screen. Okay. Catherine, can you see organic chemistry? A little revision quiz.
Yes, I can see it.
Excellent. Great. Here. Okay, guys, here we go. Right. So here's question one. Question one, what is the molecule C3CH, CH2, CH3, CH2? Here are your possible answers, so you don't have to work it out yourself. It could be ethane, it could be propane, it could be butene, it could be propene. So, what do you reckon? I'm going to give you just a moment to think about it. Oh, some people, Usharika, are feeling very keen. Don't give away the answer. Don't give away the answer, Usharika. I'm going to ask each centre how they're getting on, okay? So we'll see. So I'll give you just another moment. If anybody's trying to draw it out, some of them are more difficult than this. I'm starting quite easy, I think. I hope quite easy. Okay. Okay, good, excellent. Silver Spring have the answer. And the answer to question one is D. The question was, which one is this? And the answer is D. And it's pretty obvious. Now, if you needed to draw it out, that's fine. Usharika were showing me 4 fingers. That's absolutely right. If you got D, you give yourself 1 mark. Okay, here's another one. What is the molecule CH3CCCH3? CH3CCCH3. Now, it might help for you to draw it out. Sometimes drawing them out is really, really good idea. Have a look at it. I'll give you the options. I'm glad that some of you are drawing it out. Here are the options. Is it A, butane? Is it propane? Is it butene? Is it butene? Now, really, you might need to draw it out. Have a chat with your neighbour if you want. Genesis are pretty sure they know the answer. Oh, they're feeling quite cool, and we're feeling quite clever today, aren't we, Genesis? Yes, we're feeling quite good. Put your fingers down. Put your fingers down. You're giving it away to all of Usharika. Okay. Glory, have we got any ideas? Glory are going for B. Silver Spring, do we know? Do we have an idea? Kabiro, do we have an idea? Okay, well, Silver Spring are going for C. Let's see what the answer is. The answer is C, and the answer is C because the two carbons in the middle must have a triple bond, and a triple bond makes it an alkyne. Okay, question 3. Here's another one. What is the molecule CH3CH2CH2OH? CH3CH2CH2OH. Some people are going, oh yeah, I know that already. Some people are going, don't let me near chemistry. I want to go and do English and biology and maths. No, I want to do physics with Professor Dye, the crazy man. Here are your options. A, oh, well, you're missing something there, Silver Spring. Is it propan-1-ol? Is it propanoic acid? Is it butantuol? Is it butene? Now, if you get a little bit logical at these sort of things, put your finger down, Usharika. If you get a bit logical, count the number of carbons. I'll tell you what, Genesis, in my country, if you show that number of fingers in that way, that's pretty rude. But we're not going to worry about it. Glory, I missed that. Show me it again, please. Glory. I can't see it yet, Glory. Oh, Glory is going for B. Some people, Kabira and Silver Spring, are going for A. Let's see. Okay, the answer to number 3 is it's A. Give yourself another point. Good. Propan-1-ol. Oh, good for drawing it out, Asharika. Well done. Very good. So it's got 3 carbons, which means it must be prop. And the OH makes it an alkanol. That means that it has to be propanol, and it's on the first carbon, and therefore it's propan-1-ol. Here's one more naming question. What's the molecule of CH3, CH2, COOH? COOH. Oh, where have we seen that today? Oh, well, it's behind me on the wall, but luckily you can't see it anymore. Okay, and is it propan-1-ol, 3 carbons, propanoic acid, propan-2-ol, or propane? Propan-1-ol, propanoic acid, propan-2-ol, propane. How are we feeling? Genesis is going, oh, I don't know this one. Oh, gosh. Oh, well, I wouldn't do that. Oh, we've got 2 different answers already. We've got some right answers. That's very good. Okay, let's see what the right answer is. The right answer is B. Give yourself a point for B. Look at it again. CH3, CH2, COOH. That's 3 carbons, so it's got to be prop. That doesn't help us. But COOH, 2 O's, makes it an alkanoic acid. Get used to looking for the COOH and you'll be all right. Okay, well done. So the question is, so far, how are you getting on? Have you got 4 out of 4? Has anybody in there got 4 out of 4? Show me a thumbs up if you got 4 out of 4, because if you have, you're a bit of a genius. Ooh, 1 or 2. 3 out of 4 is very, very good. If you've got 3 out of 4 or 4 out of 4, you are amazing. And you should just take the examination now. If you've got 2 out of 4, perhaps it's a time for a little bit more learning when it comes to the exam. If it's 1 out of 4, and if it's oh dear. If it's 0 out of 4, you're going to have to try quite a lot harder. Okay, next question. What molecule could I start with if it was going to be oxidized to form CH3, CH2, COOH? So what oxidizes to make, that's an alkanoic acid, isn't it? COOH, that's an alkanoic acid. So would it be propan-1-ol, propanoic acid, propan-2-ol, or propene? Now that's where that thing on the board behind me is useful, because oxidation of something produces an alkanoic acid. Is it a propan-1-ol, propanoic acid? Well, no, there is almost always a really silly answer in one of these. You wouldn't oxidize propanoic acid to make itself. That's just silly. So the other 3 are all possibilities. Is it propan-1-ol, 2-ol, or propene? What do you think? Have a bit of a think. Asharika are pretty sure that it's propan-1-ol. Well, are they right? Here's the answer to question 5. It's A. It is propan-1-ol. And the reason for that is that every time we've got COOH, it's an alkanoic acid, and they are formed by oxidation, just by the air sometimes, of alkanols. Right. Question 6. We're nearly halfway through. Good heavens, already. What chemicals could you use to oxidize an alkanol? In other words, I've got my alkanol. I'm going to turn it into an alkanoic acid. What chemicals could I use? Here are 4 options. 4 options for doing this. Ready? The first one is K2Cr2O7 and dilute sulfuric acid. The second one is nitrogen, which we can get, as we know, from the air. The third one is zinc and dilute sulfuric acid. And the fourth one, D, is KMNO4 and dilute sulfuric acid. Have a think, have a talk with somebody else. Share your ideas with somebody else. It's really important that you don't just keep these things to yourself, but you actually test your knowledge with somebody else. It will really help. Okay, so what do we think? What could we use to oxidize an alkanol? K2Cr2O7, nitrogen, zinc, KMNO4. We've got some answers. We've got some answers coming in. A, B, C, D. We've got a right answer for Oshirika. Glory, hold it a little bit stiller. I can't see your writing bit at the moment. Silver Spring are going for A. Gloria going for C. Let's have a look at the answer. The answer is... oh, it's A or D. It's A or D. Both A and D are oxidizing agents. Alkanols can be oxidized using orange. If you remember from last time, I said try to remember the color. Orange potassium dichromate and purple potassium manganate. Okay? If you didn't know this, write it down. I will be sending you this PowerPoint so you can have a go yourselves. Okay, question 7. Let's see what question 7 is. I want to make an alkanol. What could I start with? I want to make an alkanol. What could I start with? Could I start with an alkane, an alkanoic acid, an alkene, or an ester? I want to make an alkanol. This is where that thing on the board behind me is important again. If I want to make an alkanol, try and remember the direction of the arrows. Silver Spring say A, Ushirika say possibly C. Genesis are saying C. Well, they're saying, are saying 1, which is A, I guess. I presume so anyway. The answer for making an alkanol is I have to start with an alkene. An alkene can be hydrated. I'm sorry, Kabira, you got it right. Well done. I didn't see it before, but you got it right, so it doesn't matter. So the answer is C. Alkenes are hydrated to form alkanols. Okay. Question 8. Only a few more. Write an equation for the hydration of ethene. Write an equation for the hydration of ethene. So ethene is C2H4, and we're going to add water to it. So it's going to be C2H4 plus H2O equals what? Makes what? C2H4 plus H2O becomes what? This is quite a bit harder. This is quite a bit harder. We've only got about 15 minutes left and only about 5 questions left, so these must be getting harder. Has anybody got any ideas? An equation for the hydration of ethene. That's nearly very good, Silver Spring, but it doesn't form ethane. It doesn't form ethane. If you remember from my picture behind me, an alkene with water forms an alkanol. So if it forms an alkanol, let's have a look at it. Here's the answer. C2H4 plus H2O goes to C2H5OH. What's rather important about this is that this is simply an addition reaction. Alkenes react by addition. They are just added together. So C2H4, the double bond breaks, the hydrogen joins on one and OH on the other. C2H4 plus H2O goes to C2H5OH. Question 9. Write an equation for the oxidation of ethanol to form ethanoic acid. Now, we normally write an O in square brackets for an oxidizing agent. So you will write ethanol's formula plus O in square brackets, and then an arrow or equals the formula for ethanoic acid, and there is one other thing formed. If you count the number of carbons and hydrogens, you might work out what it is. So it's going to be C2H5OH plus O in square brackets equals CH3COOH plus something. Who's got an idea? Some of Usharika are writing, some of Kabiro are writing, some of Silver Spring are looking a little bit, oh my gosh. Oh, very nearly Silver Spring. Just think what the alkanoic acid is, what ethanoic acid is. Remember, all acids have COOH. So if it's 2 carbons and it's got to have COOH, it will be CH3COOH. So listen, my equation must be C2H5OH plus O in square brackets equals CH3COOH plus something. Here's the answer. C2H5OH plus 2 O's in square brackets goes to CH3COOH and water. If you look at CH3COOH, it's got 2 fewer hydrogens than C2H5OH. So those 2 hydrogens have to go somewhere and they turn into water. That's quite difficult. That is one of the most difficult things we do. Okay, that is the oxidation of an alkanol to make an alkanoic acid. Very last few questions. So here's question 10. I want to make an addition polymer. What should I start with? An alkane, an alkanoic acid, an alkene, or an ester? I want to make a polymer, an addition polymer. What do I start with? A, B, C, or D? A, B, C, or D? Addition polymer. What do I start with? A, B, C, or D? Silver Spring and Usharika are both going for the same letter. Very good. Genesis are going for something different. Genesis, you're going for A, are you? Are you going for A? Think about it. Addition polymer has to start with what? What did we say? I was just doing it behind me on the board. Addition polymers, they have to add together. So what do they need in their molecule? Think about it. And the answer is C. The answer is C. Look at the question again. Addition polymer, and if it's an addition polymer, it has to start with an alkene. Alkanes react with almost nothing. Alkanoic acids, esters, we haven't come across those making polymers. Addition polymers are made from alkenes. Last 3 questions. Question 11. How are you doing now? If you're anywhere 70% over, you are amazing. And I mean actually really amazing. If you're somewhere over half marks, you are very good indeed. And you will do fine in the examination. If you have 30% or over, you could still pass. In other words, you are still doing enough to be able to pass this examination. If it's 0 to 30%, in other words, you've only got 3 out of the 10 so far, I hope you will work a bit harder when we come to the examination. Now, I want to make that polymer. Look at the polymer. Remember, it's 2 carbons in a line with the bits on the side. So what could I start with? I want to make that polymer. Is the answer propene, ethene, butene, or propanol? Well, it's an addition polymer. It doesn't tell you that, but it is an addition polymer. Is it 3 carbons, 2 carbons, 4 carbons, or an alkanol? Look at it and try and see what the repeating unit is. How many carbons are in the repeating unit? Usharika were getting courageous there and then suddenly went, oh no, hang on. How many carbons in the repeating unit because that is how many carbons there will be in the monomer. So how many carbons do you think it needs? The repeating unit count, and the answer is A. There is the repeating unit. Oh, Sharika, they were. Oh no, I knew that. I knew that. There is the repeating unit. Look, just find it. 2 carbons with some other bits off it. That is the 3 carbon unit, and therefore it must be ethene. Sorry, propene. Okay, that's very important that you can do that. Okay, so there it is. There's the polymer. Look for the 3. Must have been propene. What is needed for the hydration of ethene to form ethanol? Well, it's going to be water because it's hydration. But what conditions do we need? There were 3 things. If I want to turn ethene into ethanol, there are 3 things I need. Apart from water, which I have to put in, it needs to be steam, so it has to be quite hot, but there is a temperature, a pressure, and a catalyst. And we did it last time, and see if you can remember it. Ethene plus water to ethanol. We did it last time. If you weren't here, for instance, Gloria, I don't think you were here for some of it, then don't worry. But this is something that you just have to try and learn. It's 2 numbers and a catalyst. Does anybody remember? Hydration of ethene to ethanol. Here we are. Well, it's steam, 300 degrees Celsius, 70 atmospheres pressure, and phosphoric acid as a catalyst. What was it? What was it? Try and remember now. 300 degrees, 70 atmospheres, and a phosphoric acid catalyst. Last question. An addition polymer is made from propene. If the RMM of the polymer is 525,000, how many propenes were needed? So propene is C3H6. Try and work it out. How many propenes would join together to make a polymer with an RMM of 525,000? Take a moment. You might need a calculator. So you work out the RMM of the monomer. Come on, Glory, don't give up yet. You can do this. I just showed you how to do this. So if RMM is 525,000 and it starts with propene, what are the answers? Here are 3 options. 525,000, 10,000, 175,000. Well done, Oshirika. 12,500. Which one is it? Oshirika think they know. Oshirika are feeling quite cool. Oshirika are feeling quite clever. Well, one of them is anyway. So come on then, Genesis, you can do this. 525,000 RMM. How many propenes? Work out what propene weighs, what its RMM is, and you can do it. And the answer is D. The answer is D. Why? Well, because each propene, which is C3H6, has an RMM of 42. If the polymer's RMM is 525,000, then it is 525,000 divided by 42, which is 12,500. And that is, ladies and gentlemen, the end of the quiz. Okay. Did anybody do very well on those? Because they're quite hard. They're really quite hard. They're really, really quite hard. Okay, you did okay. Okay, well done, Glory. So, how many people feel that they did really, really well, or really quite well, or not bad at all, and then not very well, or pretty terrible? So, who felt, yeah, I did pretty well? Who went, oh, yeah, pretty well. Yeah, good, well done. Who went, okay, about half marks, a little bit less. It's okay. Okay. All right, Glory, nice one. And how many people went, oh no? How many people went, ugh, ugh? Okay. All right. Well, we all know what we have to do when it comes to examinations. I will put this onto YouTube. I will send it to you so you can look at it again. These are all questions which have come up before on KCSE examinations. Okay, every single one of them. So they are types of questions which you might have to answer. Try to remember this behind me to practice using that sort of thing. It will make life much easier for you when you come to revising and learning things. But now, with the time 1 hour after I started, I will ask if anybody has any questions. They can stay, but otherwise I will say asante and well done to those people who tried to answer the questions. There are many of you. Thank you very much indeed. And I will say get out and go and have a nice evening. It's very nice to see you. And bye-bye. If you want to stay and ask a question, just stay for a minute. Headmistress, do leave. That's very kind of you being here. But okay, so bye-bye, Genesis. Bye-bye, Usharika. Bye-bye, Glory. I don't know who else is still around. I don't know if Silver Spring are still around. They normally have a question they want to ask. But if anybody has a question they want to ask, just hang on just a minute. Silver Spring are just coming on. Glory, I thought you were good attention. Well done. I really like the way that you tried to do it. I know it was quite hard, but I like the way you were trying to focus it, and it was very good. Genesis, good effort, really good effort. Usharika did fantastically well. Silver Spring will have a question. We're not taking any questions on the solve process. Right, switch the microphone on if you want, Silver Spring. Or show me it, write it down and show me it. Up to you. Oh, you put something in the chat. Hang on. Somebody's put something in the chat. Great lesson. Oh, thank you very much. Thank you very much, Headmistress. I hope that some people learned some things and at least tried to answer the questions, because that is the skill. Really just trying. Just trying makes a lot of difference. Okay, any questions? Because otherwise I'm going to stop recording now anyway.